Okay, so this is a confidence interval, and it's a confidence interval for a mean when sigma is known. And it's about hummingbirds, so hopefully you've read through the problem. I got from the problem that the x variable is, x is the weight, the average weight of the birds, and things like that. X bar is the average weight. So the variable of interest is the weight of the hummingbirds, but it's a normally distributed variable. It has a sample mean of 3.15 grams and a population standard deviation known to be 0.33 grams based on previous studies. N in the sample is 15. So this is going to be a z interval if you're doing it just using the calculator, but I'm going to show you how to do it by hand. And it says find and interpret an 80% confidence interval for the average weights of the hummingbirds. So we're going to do that. Always, step one is to just do your error. Your different books call it different things. It's called the margin of error, or also your error of tolerance. It's basically just how much are you willing to be wrong. So the first thing you need to do is find a z critical, or what I like to call a z confidence in value, z confidence. So I'm going to go to this little quick guide table here showing me critical values with confidence intervals. When I'm looking at a 80% confidence level, I've got a critical value of 1.28 on the z. So 1.28 times the sigma given, 0.33, divided by the square root of n, which is 15. Work that out and we get 0.1090632111, and that's the margin of error. Okay? And the calculator in my grapher, it was getting 0.109195. So just slightly different margin of error, but that has to do with rounding and things like that. So that's the difference. After you get your error and you're calculating by hand, you have to take the sample mean, 3.15, minus the margin of error. So minus all of this good stuff. Boop, boop. And less than mu, less than the sample mean, plus the error. And mu is trapped in the middle. So we're getting our interval right here. Looking around for a calculator because I haven't calculated this guy yet. So get in my home screen here and we'll do 3.15 minus all this good stuff. We get a lower bound of 3.04094, and when we do an upper bound, we get an upper bound of 3.25906. So based on the evidence, this is our interpretation, step 3. We need to interpret the interval, make intelligent sounding sentences. We're going to be 80% confident that the true population mean, let's call it a weight, lies in the interval. Let's go ahead and round for simplistic purposes, 3.04 to, let's do 3.26 grams. Okay, now I always tell you how many decimals I want you to round to, but a rule of thumb usually used in mathematics is whatever decimals they gave you in the problem, then you should report the same number of decimals back. In physics and maybe other mathematics courses, depending on your instructor, sometimes they wanted you to give back one more decimal place than what was given to you. It just kind of depends. But I will always tell you when I really care. So now they want you to find a sample size necessary for an 80% confidence level with a maximal error of estimate, that's another word for E, of 0.08 for the mean weights of the hummingbirds. So your error of tolerance, your margin of error, or also called your maximal error of estimate, has many names, is 0.08. You want to be 80% confident, and you've got a sigma given to you. So in estimation formula, right here, we're just going to plug in z confidence. If we had a different confidence level, we'd go back to that table and find the corresponding critical value. we're using the same confidence level, so I can steal the one I looked up here, because it's the same one. 1.28 times sigma 0.33 all over not the square root. How about just e, which is 0.08? And then don't forget to square it, okay? People often forget to square it. So when you work all that out, I'm getting about approximately 27.878, and let's round this up to, we need to get at least 28 birds. Okay? So n needs to be at least approximately 28 birds. And that's finding the sample size. And you should do all of your other confidence intervals that use a z similarly to the way we did part A, and you should estimate that sample size when you've got the normal distribution and the z going on like we did part B. So if you have any questions, let me know.